Hello, my name is John Gorman. Welcome to Lab 1, Constant Velocity. So to start, we're going to talk about the purpose of the experiment. The purpose is to observe and analyze constant velocity motion in real life and compare it to a computational model which predicts motion. So to do this, we're going to need a system. The system we chose is a lacrosse ball, and our surroundings are everything else. And our key assumptions are that the net force acting on the ball is 0. This means that there is no friction, no air resistance, and that the force of gravity equals the normal force. As we can see over here, all the forces are balanced in our net force diagram. So to understand what's going on in the lab, we're going to need to understand Newton's second law. Newton's second law is our equation on the left. The derivative of momentum according to time is the net force, or the change in momentum over the change in time is equal to the net force. We also know that the change in momentum is equal to mass times the change in velocity. By using these two equations, we can derive the velocity update formula, which is extremely important in predicting motion with constant forces. However, our net force is 0. So this whole term cancels out, and we find that VF equals VI, and when VF equals VI, it also equals V average. We can then use these velocity values and plug them into our position update formula in order to predict the motion. So to start, we're going to talk about what we did in Tracker. So we uploaded a video of our lacrosse ball rolling across the screen. And to actually get a velocity from this, we need to plot points. So each frame we plotted where the center of mass where the ball was, and this gave us a bunch of position versus time points, and we plotted that on, or Tracker plotted that on a graph up in the top right corner. We then use these values that we found from Tracker in order to develop our computational model. So to actually make the computational model, we're going to need to find some initial conditions first. We'll start with position. Position is a pretty easy one to find. It's just the first xm value because that is where the ball started. Velocity, on the other hand, is a little bit more complicated. We need to use the fact that the velocity is the derivative of position, which means that the velocity is equal to the change in position over the change in time. We can then use this fact to set up an equation using our values over here and solve. So that gives us 0.4613 meters per second as our velocity. Now that we have our initial conditions, we can finally make our computational model. To start, we can see that the initial conditions we found on the last slide are in the top right corner here under ball.pause and ball.vile. We can also see that delta t is equal to 0.033 seconds. This is because Tracker runs in 30 frames per second, and each frame was 0.3033 seconds away from each other, making delta t our time step. Fnet is 0, again, making the second part of the velocity update equation 0, allowing the ball velocity to stay constant throughout the entire time the computer program runs. And then finally, iterative calculation for position using the position update formula. It's in a while loop. So each time it'll run through, it'll update position, and then it'll update the time, and then it'll spit it back out and give us a coherent graph and points to plot. Here we can see what it looks like when the program runs. We can see the ball moving to the right with a positive position versus time graph and a constant velocity versus time graph. Now that we have our results, we can finally compare them. They're very similar at first, but they diverge soon afterward. Why? Well, the big reason is that there are external forces acting on the ball. Tables have friction and air resistance exists, which means the ball is getting slowed down in the x direction, which is the main reason for the dip. There could be little reasons though. There could have been a tracking error. I could have clicked a point that is not the center of mass in the ball, but very close. And then there could have been rounding errors in my calculations as well. So finally, we're going to discuss some additional questions. First of all, what if we flip the axes from x plus to x minus? Well, not much would happen. The signs of the results would be flipped. Well, there'd be a negative velocity, but the ball didn't change the direction it's moving in, only the coordinate system changed. So this would result in a negative linear slope on the position time graph, while the magnitude of the slope remains the same. So the magnitude of the velocity does not change because magnitude is always positive. On the other hand, is it possible to tell how many forces are acting to give 0 net force in the case I observed? Well, there is a net force acting on the ball in the x direction, so it doesn't really apply to that case. In the On the other hand, in the y direction, the net force is 0, and we can tell that there are at least two forces acting on it. There's gravity and the net or the normal force, but other than that, you can't really tell. So, thank you so much for listening, and have a great rest of your day.